Here is Miss Walsh, and today we're going to do binomial distribution. Ooh. Okay, I have a biased coin for which the probability that it's of getting ahead is 0.2. So it's not a 50-50 coin, but it's one that's maybe heavier on one side. All right, let's flip the coin 4 times. List all the ways that we could get 2 heads. Well, all right, we could get head, head, tail, tail. We could get tail, tail, head, head, tail, head, tail, and then do the same thing the other way around, and then you would see that you would get 6 ways in total. Okay, hence find the probability that when you flip it 4 times that you would get exactly 2 heads. All right, well, for each one of these possible outcomes, for example, head, head, tail, tail, what would happen? Our probability of getting ahead is 0.2, right? Which means the probability of not getting ahead, same as a tail, is 0.8. So head, head, tail, tail is going to be 0.2 times 0.2 times 0.8 times 0.8. All right, what about tail, head, head, tail? Well, actually, this is going to be 0.8 times 0.2 times 0.2 times 0.8. And what you see is you actually get the same answer. And since we have 6 possible ways of doing this, then our total probability of getting 2 heads is going to be, twice we get the head, doesn't matter in which order, and twice we fail to get the head, and then that's going to be done in 6 different combinations. Okay, so what we end up with is approximately 15.36. Okay, let's do another one, and you will see what emerges. All right, when taking a penalty, I know from the past experience that the probability score is 3/4. I take 5 penalties. All right. Okay, so our penalty is our success here, right? This is our success. Okay, well, what can happen that if you score a penalty 4 times, you could maybe like score, and then not score, or maybe you did score, not score, and so on, right? So you can tell, all the way down to you failed the first time, and then you scored. Altogether, you would have 5 possible outcomes. All right, find the probability that we score 4 times and 5 penalties. All right. Okay, so what's going to happen? Well, what's going to happen is we are going to score a penalty 4 times, and then we're going to miss once. And that can happen in 5 different ways. So it's like picture a humongous tree diagram where you would be adding all of those up. Okay, so how are these scenarios similar? Well, hopefully you can see that in order to find the probability, it's always the number of ways that to get the desired outcome. Desired outcome times, and then it's going to be times the probability of success, and then you times the probability of failure to however many times you want to succeed, right? So how many successes and then however many failures. This, by the way, will always add to the total number of trials, right? So if you fail 4 times, score a penalty 4 times and fail once, in total you took 5 penalties, okay? The sum will always hold. Okay, extra assumption you need in order for this to work, of course, the events do need to be independent. Because obviously, if you're getting tired after some penalties or something like this, then those probabilities won't hold anymore. Okay, so these events are very, very common. And so we actually have a cool little calculator app to get them for you. So yay, you do not have to do this every time. So in order for this to do, right, what makes something binomial is when you have 2 outcomes. Okay, so either it's a success or a failure. You're doing the same experiment over and over and over, okay? And as we said before, what's really important is that it is independent. That's what qualifies a distribution as being binomial, all right? So we're going to try when I'm going to show you how to do it with the app. It's going to be super cool, okay? Right. A coin is flipped 4 times, and the probability, let's change this to 0.2, okay? Let x be the number of heads. We want that x is 2. This is actually the same as our previous question, right? Okay, so what we have here is we have a random variable, binomially distributed, okay? So remember, this means binomial, and then this is always the number of trials, and this is always the probability. This is always what you write, okay? That's your method point for recognizing binomial distribution. So here we're going to toss a coin 4 times, and the success is 0.2. What makes this binomial? You're tossing a coin over and over and over. So it's the same experiment, okay? They're independent. You're doing it, and either you get that head or you don't. All right, so what do you do in the calculator? If you want the exact number of trials, then we're going to go to tam-ta-da-dam. So do this with me. Don't just watch me. I'm not Netflix. Okay. Just go to the toolbox, and then we're going to go to probability. Then you're going to go to this density right now, okay? Density, and then what we're doing is we're doing binomial distribution, okay? This little help button is also helpful because it tells you in what order to put things. So this is your total number of outcomes, this is your probability, and K is your number of successes. So we're performing the experiment 4 times. Our probability of success is 0.2, and we want exactly 2 heads. Tam-ta-da-dam, looks familiar? That's because we did it before, okay? So on our HP prom, we have binomial, and then 4, 0.2, 2, and there's your answer. Of course, it's the same as in the previous page when you did it the long way. It's just so that you understand where the theory is coming from, right? The calculator is doing something mathematical. Let's try one more. I love probability. All right, 20% of adults in town are left-handed. Find the probability if a sample of 8 people are selected that 3 are left-handed. Okay, is this binomial? Yes, because either they're left-handed or not, okay? So again, over and over, they're independent. One person's handedness is independent of another person. So this x variable is binomially distributed with a total number of 8 trials and a probability of success. So success here is defined as being left-handed, okay? Alrighty, let's do this, okay? So probability that it's exactly 3 is going to be rushing a little bit, is going to be, so we're going to go binomial. So again, toolbox, probability, density, binomial, alrighty? And so, hey, 8 times, hey, 0.2, and I want exactly 3 left-handed people, okay? And you get 0.147. Okay, you can do the same thing with the 2 hands. So this is where you could pause the video. You should do exactly the same thing. You can just write over it. You should get this, okay? So check that you do. If you do, then you can give yourself a high five. All right, okay, this is a binomial situation, 8 times probability left-handed. What might the person conducting the survey not make sure the responses are independent? Maybe, no relatives in case it's genetic or something. Okay, so now we move into another part of this, which is when events are done, when they are cumulative, okay? So when you're going to be happy with more than one outcome at the same time. What do I mean? Okay, so the cumulative probability can be found using the same. What does cumulative mean? Remember, cumulative means adding up to and including, right, from the first unit. At most are left-handed. At most means that you need the left-handeds to be 2 or less. So you would be happy with no left-handed people, or 1 left-handed person, or 2 left-handed people, okay? You can do these separately, but, we don't want to. We ain't got time for that. Okay, so what we're going to do instead now is we're going to go back to the toolbox, probability, and now you're going to be adding up more than one outcome that you like. So what you're going to do is you're going to go to cumulative. Again, it's binomial. And you're going to be like, hey, 8 outcomes, still 0.2. And I want it up to 2 and including, okay? So you can see, so what is this? So what this 7,969. What this is the calculator does up to and including, okay? So it already did this separately and then adding them up. Isn't that cool? Okay, so be careful with the wording in this unit, okay? Fewer than. Okay, if it's fewer than 2, you're not happy with 2. So what that means is you want it to be less than 2. Well, how is the calculator supposed to know if you're including the 2 or not? The calculator doesn't know. So what we're instead going to do, so you're happy with 0 or 1. So the way that we're going to represent that is we're going to represent that as the probability of x's less than or equal to 1, okay? So whatever you type into the calculator, always do the less than or equal sign, okay? So again, look at me cheating. I just pressed enter because what I'm going to do now, just going to write over it and boom, 0.5033 or 3 if you're doing 3 significant figures, okay? All right, so it can also do in between. So for example, find the probability that you have 2, 3, or 4 people that are left-handed, okay? So what you want is you want x to be between 2 and 4, okay? You do exactly the same thing, okay? So you're gonna go to binomial CDF, and we're gonna type in R8, R 0.2, and then we're going to do the from. So this is from this, and then it's to this. Alrighty, so ready? Boom, click. And then, so remember, always the number of trials, then the probability from and to. Okay, and again, so what the calculator's done here is the calculator has added the probability of getting exactly 2, exactly 3, and exactly 4, okay? So we had at most, we had fewer than, and now we have more than. More than 3, be careful, okay? People get so caught up with the wording. More than 3 means that you're happy with 4, 5, 6, 7, 8. So what you want, remember the calculator has to include that boundary. So what we're gonna do is we're gonna go from 4 up 4, 5, 6, 7, 8. Okay, so ready, click, and we're gonna go, hey, can you give me the probability from 4 to 8? Okay, and so you end up with a really small probability, 0, 5, 6, 3. This should make sense because the probability of being left-handed in the first place. Okay, I gotta go, so I'm gonna cut this short. Can you see if you can get these values? Alrighty, bye.